Let me move on to my third character, Ibn al-Haytham. Now, he's known to the Latins as al-Hazan, and that's the name under which he is most commonly called. He's yet a generation further on. He is 10th and 11th century, born about 965, died in 1039. Well, he did quite a lot of things. He criticized, for one thing, the disjunction between Ptolemaic cosmology and physical principles. Remember that there are some problems with Ptolemy. He moves the Earth out of the center of the universe and makes the orbits of the planets eccentric. He has epicycles where the planets are on this epicycle moving around a point on the deferent, and there's nothing at that point. And so there are problems when you try and relate the dynamics of physics of the time to the Ptolemaic system. They clash in certain places, and al-Hazan was very sensitive to this and tried to work it out. He never did succeed in working it out, but he did start a discussion about this problem that continued in the Islamic world for several centuries. I should mention a little bit about his life, because his life is quite interesting. What does an Islamic scientist, if we want to use that slightly anachronistic word, do? Well, we know a lot about al-Hazan's biography. Some things are contradictory, but nonetheless, I'll give you sort of a compendium of the best attributed material. It's said that he was invited to Egypt by the leader al-Hakim, who reigned in Egypt from 996 until 1021. Al-Hazan was invited there because he claimed he would be able to stop the flooding of the Nile, to control the waters of the Nile. So al-Hakim brought him in. Al-Hazan took a trip up the Nile. And the further he went, the more disappointed and disillusioned he got, because he realized that the lay of the land in the upper Nile was not what he thought it was. And so the flooding wasn't caused exactly by the principles he imagined. And moreover, he tells us that as he went up the Nile, he saw these immense monuments that had been built by the ancient Egyptians. And the more of them he saw, the more puny he felt. And he realized that if the ancient Egyptians couldn't stop the flooding of the Nile, he couldn't do it either. Well, he returned to Cairo and was afraid that he would be punished for his failure. Al-Hakim was known to be erratic and a man of bad temper. And so what al-Hazan did, according to the story, is that he pretended to have gone insane. And he feigned madness until al-Hakim died. And then he was back to his normal senses suddenly. He supported himself for the rest of his life in an interesting way. Once a year, he would make a copy of the Almagest, of Euclid's Elements, and of the related texts of Euclid, and sell them. And that brought him enough money to live for a year. He was connected to the mosque of Al-Azhar, where Al-Azhar University is now, for the rest of his life. So after the death of al-Hakim, so that would be for the next 18 years. Well, considerable advancements in mathematics also occurred in the Islamic world. One of the most notable achievements was the introduction of place notation, the numerals that we still call today Arabic numerals. Now, this system was actually originally Indian, and the Arabs referred to it as Hindu reckoning. It was transmitted to Europe through a handbook written by one al-Khwarizmi, who flourished about 825. He was connected with the Baitul Hikmah, the House of Wisdom in Baghdad. He was patronized by the Caliph al-Ma'mun. A key feature of this system was the use of the zifr. Now, what is the zifr? Well, it turns out we get two English words, not just one, from the Arabic zifr. The first one is cipher, which is the figure of the numerals, but the other and more important one is zero. Right? Never before was nothing so important. Zero, as a placeholder, was something that the Babylonians, for example, in the first millennium BC, even though they had a place notation, they didn't have a place holder. So the zero saves us all kinds of confusion about knowing what places we're in. Now, al-Khwarizmi did other things as well. He wrote a book which is entitled The Book on Reckoning by Completion and Balancing, which in Arabic is al-Jabr wal-Muqabala. Now, if you listen to the first word carefully, al-Jabr, which is the origin of algebra. Al-Khwarizmi wrote the earliest known treatise on algebra, the way of solving for unknowns by completion and balancing, that is, by moving terms from one side of an equation to another and solving for an unknown. He also wrote treatises on the astrolabe and on geography. So in addition to place notation, the zero, and algebra, Arabic mathematicians also essentially invented trigonometry. The Greeks had only one function, the sine function, but the other functions were added by Arabic mathematicians, the cosine, the tangent, the inverses. These were all Arabic contributions. Well, now having gone through astronomy and mathematics, let me get to my third topic, which is optics. Optics is another area in which the Arabic world made particularly important contributions. We have to back up a little bit, though, to talk about theories of vision in the ancient classical world so that we know what the problems were the Arabs were trying to solve. The basic problem, the fundamental problem of optics was that of how do we see? How does the image of an external object, whatever it may be, a dog, a cloud, a tree, a person, how does the image of that external object get transferred to our eye? Difficult question. There are three theories to explain this in classical Greek thought, in Hellenistic thought as well. So let's start with Euclid's version. Euclid studied vision, and like most of the Greeks, like Plato, for example, he believed that there was a visual ray that emanated from the eye. This is what is called an extromissive version of vision. That is, like a man with his eyes closed that reaches out his arm to touch to see what's around him, so the visual ray emanates from the eye until it contacts an external object, and then it tells us that it's there. How exactly it tells us is never worked out. Nonetheless, this was a standard idea. What was Euclid's particular contribution was to say that it emanated in the shape of a cone, which meant that it was able to be looked at using mathematical methods. We could calculate things like perspective, that things further away appear smaller based upon the opening up, the expansion of that angle of the cone as the visual ray leaves our eye. So Euclid's particular contribution was not the extromissive version, which was common, but rather the ability to calculate things geometrically, to use a geometrical version of vision. Very Greek idea. The second theory is a little stranger. It's the idea that the atomists had. They believed that every object was constantly peeling off its external surface, and that these very thin, what they called idola or simulacra in Latin, idola in Greek, would fly off of every object and enter our eyes. Now again, there are some problems with that, which were seen fairly quickly. If we go outside and look at a mountain, we say that some simulacrum is peeling off of the mountain and flying towards us. It's mountain-sized when it leaves the mountain, but somehow it's got to get inside our eye. That's a bit of a problem. Lucretius, the popularizer of Epicurus, says that the simulacra come off the way a snake sheds its skin, for example. Well, you know, if a snake keeps shedding its skin too much, too often, all the time, there's no snake left after a while. So that's another problem with the atomist view of vision. Nonetheless, there's a significant difference here. This is an intromissive version of vision. Something's coming into the eye, not going out of it. Aristotle promoted the third version, also intromissive. He says that objects change the quality of the intervening medium, generally the air, unless we're swimming underwater, but change the intervening medium, and so change the qualities in our eye to match the qualities of the object that's being seen. Well, the Islamic world inherited all three of these theories. The visual ray theory of Euclid, which is also upheld by Ptolemy, was agreed to by al-Kindi, a 9th century philosopher in Baghdad. He wrote works on the visual ray and the reflection, the rays from other bodies, and we'll come back and talk about al-Kindi because he turns out to be particularly important when his ideas get into medieval Europe. For now, though, let's look back at al-Haytham. Al-Haytham produced a new view of vision, which combined the old intromissive and extromissive versions. In fact, he set the foundations for the way vision and optics would be handled scientifically, really down to the present day. And there's some problems with al-Haytham's system, but nonetheless, it was very a useful one. What he did was this. His view, first of all, was intromissive. It was about light coming into the eye. The thing that he did that was important is that rather than having an Aristotelian qualitative treatment of vision, that qualities are changed, and rather than having an atomistic view with all the problems of the simulacra of a mountain shrinking to come into our eye, he instead used Euclid's cone, except turned it upside down. Instead of a visual ray emanating as a cone from our eye, the light comes into our eye as a cone. What does that mean he developed? He developed a ray theory, if you will, of light, or a conceptualization of light in terms of rays. Now, because any of us who have learned optics in the modern world say, well, rays, isn't that obvious? Well, we're familiar with it, so it's obvious. It's not necessarily obvious. It wasn't obvious for the first person who came up with it, al-Haytham. This meant that he avoided the objections of the earlier theories. For example, he says, how is it possible if we go out at night and I suddenly raise my head to the heavens, does my visual ray immediately fill the entire universe so that I can see the stars? That doesn't make sense. So he got away from that problem as well, but keeping all the time the ability to deal with rays mathematically. There was one other problem he had to worry about. If you look around you, we see a lot of objects. And rays are coming off of every object in every conceivable direction, radially. How does our eyes sort that out? Well, he proposed a hypothesis about this. Turns out not to be entirely satisfactory, but nonetheless it helped him do his calculations. He said that from every point on every object, there is exactly one ray, and only one ray, that impinges upon the eye, since the eye is curved, that impinges upon the eye at a perpendicular. Now think about that. There is one and only one ray from every point on an external object that hits the eye at a perpendicular. Well, al-Haytham knew the laws of refraction. He knew that rays that come perpendicularly into a new medium are not refracted. Anything that comes at any angle that isn't 90 degrees is refracted. So his argument went like this. Any ray that's refracted is weakened and not sensed. Only the ray that comes in perpendicularly is actually sensed by the eye. Now think what that means for a moment. It means that every point is represented by exactly one ray, which impinges upon exactly one point in the eye. Therefore, we've transferred the image of all external objects point for point from the outside to the eye. It's a great achievement for al-Haytham to have done this. Al-Haytham was seen as a master in vision and in optics. He wrote not only on vision, by the way, but also on burning mirrors, those parabolic mirrors that can be used to direct solar rays, concentrate them to set things alight. Surely he, like many of his contemporaries, knew the wonderful story of Archimedes supposedly setting the Roman fleet on fire in the harbor of Syracuse, and that was, of course, one incentive for studying burning mirrors. All right. Well, what we've done in this lecture is to look at three aspects of Arabic original contributions to the history of science in astronomy, in mathematics, and in optics. In our next lecture, what we're going to look at is something that is in fact almost an Arabic original, that is alchemy. They did take some of it from the Hellenistic world, but it was developed to such a high degree in the Arabic world that we can almost think about it as an Arabic science.